Welcome to this interesting video. I introduce you to Titans from Google Research, learning to memorize at test time. Now imagine trying to read a book, but you can only remember the last 2 pages that you have just read. That's the challenge many AI models are facing today. Transformers, the AI models that we have been working with, and we have so many different models based on transform architecture. They're great at analyzing data within a limited window or context length, but when it comes to managing a huge amounts of information over time, they struggle. And do you know the reason why? Because they're like short-term memory wizards with no long-term planning. Now this is where Titans come in. These new models combine the strength of short-term attention mechanisms with a revolutionary long-term memory system. We're going to look deep dive into those systems, but you can think of Titans as the AI equivalent of the human brain. In fact, they have tried to copy the brain of human. If I am permitted to move ahead of time, I would like to state that they are using something known as surprise matrix. So think of like this: every human remembers if it's more interesting, if it's more surprising. So all these surprising things you remember for a long time, and not so important things you tend to forget. So if you're watching a movie and there is an element of surprise that stays with you for a long time, so that's one element of putting in surprise as the factor for remembering something. Now also, humans do not essentially remember everything that it is made to remember. No, we tend to forget as well. So as time passes, we forget things as well, so that we make some space for new surprises or new things that's coming to our life. So there are 2 things that this model does. First is they introduce a surprise matrix, which helps in remembering things, and then they're introducing something for forgetting as well. So let's go through this paper line by line, or I jotted down a few important lines, and then we're going to discuss this. So we are all aware of transformers. In this transformer, attention allows attending to the entire context window, capturing the direct dependencies of all tokens. This more accurate modeling of dependencies, however, comes with a quadratic cost, limiting the model to the fixed length context. Essentially, the more context you put in, the cost is quadratic. Now they are presenting a new long-term memory module that learns to memorize the historical context. How? Using the surprise element, and helps an attention to attend to the current context while utilizing the long past information as well. Essentially, they're introducing 3 memories. We are going to look deep dive into those memories, but they're calling it Titans, and they're presenting 3 variations of how this can be effectively incorporated. Now, effectively, they can scale this memory to 2 million context size with higher accuracy and needle in a haystack task as well. Needle in a haystack, basically we want to extract a particular string, for example, from a huge volume of text. So there are some standard tests called needle in a haystack test. We can go on increasing the haystack, or you can go and increasing the search area, and you want to find the needle, which is a particular phrase or a particular structure data that you can think of. There are standard methods for needle in a haystack, but it performs pretty good. Now let's go to introduction. So the primary building block of transformers attention modules functions as associative memory blocks, where they tend to store key value associations and retrieve them by computing pairwise similarities between keys and queries, as we know. Now, the quadratic time and memory complexity in terms of the context length. So we have the quadratic relationship. If you increase memory, we have quadratic cost, quadratic time, and it's very difficult for transformer architecture. In complex real-world tasks, video understanding, language understanding, long-term time series forecasting, the context window can become extremely large, making the application of transformers challenging in these downstream tasks. I have been facing quite a lot of difficulty in making this series forecasting work, in making video understanding using large language models, because it's easy to implement it for a 2 to 3 minute video, but it's a completely different picture when you are trying to implement for a 1 hour or 2 hours video. That's a completely different story. Now, again, bringing back to what we are trying to do, we are trying to improve the memory. We're trying to improve the long-term memory so that it uses that information in the real time. Now, this is not a new problem. This problem was always there, and because of that, we had MEMGPT. You can go and watch the video on MEMGPT on my channel, but MEMGPT was one trial for increasing the memory, but just essentially increasing the context length is not enough. We need to sort of give importance to some data and not so importance to some other data. Now, this paper brings exactly that. It tries to define how do we allocate importance to different information and data that is coming forth. Now, although these architectures draw inspiration from the human brain, each of which are missing. So it talks about some architecture which draws ideas from the human brain, but they are missing the crucial component for learning process, such as short-term memory, long-term memory, meta-memory attending to current context. Number 2, how these components are interconnected that can operate independently. And number 3, the ability to actively learn from data and memorize the abstraction of past history. So these are the things that we are missing in the literature survey that we have done. In the existing frameworks, we miss those things, and therefore we are trying to build an effective learning paradigm which is similar to the human brain, that are distinct yet interconnected modules, each of which is responsible for a component crucial to the learning process. Now, the memory perspective, we cannot deny, and we have to agree that memory is a fundamental mental process, and it's an inseparable component of human learning. If you cannot remember what you did in the last hour, it would be very severe for you, because you have to relearn everything. In Bollywood, we had a movie in which the character forgets every morning what he did. He forgets everything every morning. So he had, in a way, tattooed some things on his body, and every morning when he gets up, it's a new beginning. So he has to remember all those things. It's very difficult for him to survive. So this is the role of memory. It's very important. It defines who we are. It helps us to remember things. Now, same can be incorporated in the large language model as well. So this paper is an attempt to do that. Now, memory has been inspiration for many seminal research in machine learning literature. Most existing architecture consider memory as a neural update caused by the input, and defines learning as a process for acquiring effective and useful memory given an objective. The main difference between transformers and linear transformers is that the memory structure as well as the memory updating step, in which the linear transformer compresses the historical data into a fixed value matrix value memory, while transformers keep all historical data within the context length without any compression. This is the issue with transformer. It keeps everything, it keeps important to all the things and keep it within the context length. Now, even with 128K context length, it's very less if you consider the lifetime experiences. If you consider and compare with human beings how much we can remember, there is something better that we need to do. And this paper is an attempt to mimic the human brain and improve our memory. So The motivation is based on these questions. First question is, what constitutes a good structure for the memory? So what constitutes a good structure for the memory? Number two, what is a proper memory update mechanism? What is a good memory retrieval process? How to design an effective architecture that incorporates different interconnected memory modules. 5, is the deep memory module needed to effectively store, remember long past? These are the questions, or you can say research questions, that prompted them to go ahead and do the research and come out with this beautiful paper. Now, the contributions that they're putting forward is the answer to all the 5 questions that you have just discussed. They are designing a long-term neural memory module that can effectively and efficiently learn to memorize at test time. So at inference time itself, it's going to learn new things, store it, and use it for the next prompts throughout its lifetime. It also forgets things that are not important. It remembers things which have an element of surprise. Very complex, but very good. I think we're moving ahead towards AGI. Now, building upon its design, we discuss how it can be incorporated into an architecture. Now, the neural memory, we present deep neural long-term memory, and as a meta in context model learns how to memorize, stores the data in its parameters at test time, inspired by the human long-term memory system. We design this memory module so an event that violates the expectation, being surprising, is more memorable. Come again. We have being surprising, so anything which surprises you, you tend to store and remember it for a long time. So that aspect this paper is trying to copy. Now, they are also putting in the decaying mechanism as well, because of the limited memory that we have, and also considering the human brain. If you want to mimic the human brain decays as well, or the human brain forgets as well. So we need to put in the memory loss and decaying mechanism as well, that consider the proportion of memory size and the amount of data surprise, resulting in better memory management. Now, this is the Titan architecture. After designing the long-term neural memory, an important remaining question is how to effectively and efficiently incorporate memory into deep learning architecture. Now, we present Titans, a family of deep learning that consists of 3 hyperheads. Core. This module consists of the short-term memory and is responsible for the main flow of processing the data. We have the long-term memory. This branch is the neural long-term memory module that is responsible to store, remember long past. And persistent memory. This is the set of learnable but date-independent parameters that encodes the knowledge about the task. Finally, as a proof of concept, they present 3 variations of Titans as incorporating memory as a context, as a layer, as a gated branch. Now, the experiment results that they have done, they conducted experimental evaluation on language modeling, common sense reasoning, recall intensity, needle in a haystack, time series forecasting, and DNA modeling tasks, each performing very good. Now, Titan outperforms transformers with the same context window and show competitive performance with transformers that use the entire context. So, Titans are able to scale to 2 million context window size as well. Isn't this great? Let's move on. So, we are talking about this long-term memory. So we have this. To design a neural long-term memory, we need a model that can encode the abstraction of the past history into the parameters. A simple idea is to train a neural network and expect it to memorize its training data, but that is not very good. Memorization, however, has always been known as an undesirable phenomenon in the neural networks, as it limits the model generalization, causing privacy concerns, results in poor performance in test time. Moreover, memorization of the training data might not be helpful in test time, in which the data might be out of distribution. We argue that we need an online meta model that learns how to forget and memorize the data at test time. The model is learning a function that is capable of memorization, but it is not overfitting the test results or training results, resulting in a better generalization at test time. So this is the learning process, the surprise that we've been waiting for to train a long-term memory into the parameters of the long-term memory. As discussed earlier, an event that violates the expectation or what causes surprise. Surprise is more memorable than for humans. So, inspired by this, a simple definition of surprise for the model is put here. So this is the element of surprise here. Now, we have two things here. Past surprise, which measures the surprise amount of the very recent past, and momentary surprise, which measures the surprise of incoming data. So what do you think is more important, whether it's a past surprise or it's a momentary surprise? I think the momentary surprise is more important. Okay, so we have the forgetting mechanism as well. When dealing with very large sequences, it is crucial to manage which past information should be forgotten, even with a deep or very large matrix value memory. We use an adaptive forgetting mechanism that allows the model to forget the information that is not needed anymore, resulting in better managing the memory's limited capacity. That is pretty good. Now, we have three things here. So you can see this memory as a context architecture here. So we have the core memory here, which is the in-context learning here. We have the persistent memory here, which is fixed, and we have this contextual memory here, which is changing in test time, which is the learning memory here. So the core memory uses both the persistent memory and the context memory, and after it passes through the attention, it updates the contextual memory or the neural memory here as well. So this is how we use memory as a context. Now there are other two parts as well, where we have memory as a gate architecture here, and we have one more, memory as a layer architecture here. So these three architectures, they did some experiments on different baselines. Well, the important one is needle in a haystack, and you can see that we have this model. So Titans here, we have these three variations, MAC, MAG, MAL, and you can see that these are performing pretty good in so many different benchmarks here. Now that is amazing. It would be good to test this out rather than looking at the benchmarks, but let's see if we could test this out. But this is how it's done. Now they're using the ruler benchmark for the NIAH, which is needle in a haystack task, and they are increasing the sequence of length from 2K till 16K. So for example, you can see here the context length increases, or needle in a haystack, the hay increases, the haystack increases, and you can see that the complexity increases as well. So from needle in a haystack PK to needle in a haystack N, needle in a haystack W. So this is more complex than N, it's more complex than PK. And you can see that when we go row wise, and you can see that train test this TTT model, you can see that the performance goes on decreasing. Mamba 2, you can see the performance goes on decreasing. It's not able to find that particular phrase in the needle and haystack experiment. You can look at delta net. You can see that it's not able to find in the 16K context. In SNIAHW, it's not able to find that thing. But for Titans, you can see it's pretty good. There is so less depreciation in the findings, in the accuracy. You can see this accuracy percentage. You can see this is the Titan MAC, and you can see that accuracy doesn't decrease that much even when the sequence length goes to 10 to the power 6. That's a million. And on the right, you can see the fine-tuning setup. You can see that Titan's MAC fine-tuning, it again is better than all the other models. And when we say all the other models, we have our GPT-4 and GPT-4o mini as well. And that's an important thing to note. We have mini and GPT-4o here, and here we can see we have this GPT-4o mini here. So that's an important thing. We have seen that there is significant drop in performance while increasing the sequence length, but not for Titans, because this is amazing. Now, they have tested with different models, and they found it pretty good. Long-term forecasting, you can see that the baseline results are highlighted here, and you can see that the very good performance. The effect of deep memory, we have good performance here as well. Time series forecasting shows good results as well. DNA modeling, again, it's pretty good. We find that LLM is competitive with state-of-the-art architecture across different downstream geometrics. But I would really want to test this out, but this is an amazing model. The concept is amazing. Now let's go through the conclusion, and then we are going to wrap this long video. Now in this paper, we present a neural long-term memory that is a meta in context learner, learns to memorize at test time. The neural memory module is a recurrent model in nature and is adaptively memorizing tokens that are more surprise or close to surprising tokens. Comparing to the modern recurrent models, it has more expressive memory update and storing mechanism. Using this memory, we present Titan architecture and 3 variants: memory as a context, memory as a gate, memory as a layer. Our experiments evaluation on diverse tasks validate that Titans are more effective on transformers and recent modern linear recurrent models, especially for long context. Now Titan can scale up to 2 million context size windows with better accuracy and baseline. I hope it's clear. And Titan is implemented in Python and JAX, and we intend to make the code we train available soon. We are going to test this out, don't worry. But this is an amazing paper. If you have time, just read through it and you can see it's pretty amazing. But again, in summary, we are trying to model our human brain because this is what we have, and that's unique. This is the first step. It's not the first step, but it's not even the best step in trying to mimic the human brain. We have so many things to learn, but this is a very noble step from Google Research. Now, if you want to learn more about Phi 4, which is a very good model, check out this video. If you want to learn about Llama V01, which is a very good vision model, you can check out this other video. But if you don't like any one of these, you can go to my channel and watch out for other videos. Amazing videos that I create. Join my Patreon, subscribe, and fill in the blanks. Thank you and have a nice day.